Look at your hand. The atoms, the molecules, the very fabric of reality itself. What if I told you that everything you're seeing right now, your hand, this screen, the stars above, is fundamentally two-dimensional information projected into three dimensions? That the universe itself might be the most elaborate hologram ever conceived. In 1997, physicist Juan Maldacena proposed something that seemed impossible. He suggested that our three-dimensional universe, with all its depth and substance, might be encoded on a distant two-dimensional surface, like a cosmic holographic projection. Most scientists dismissed it as mathematical curiosity. They were wrong. Over the past 2 decades, evidence has emerged from black hole physics, quantum experiments, and the very structure of spacetime itself. Evidence that refuses to go away. Evidence that grows stronger with each new observation. The implications are staggering. If true, everything we understand about reality, about dimension, about the nature of existence itself requires complete reconsideration. Today, we journey through evidence that challenges everything we thought we knew about the fabric of reality. Dramatic pause. Prepare yourselves. We begin.
The story begins not with the holographic principle, but with a problem that haunted Stephen Hawking for decades. A problem so profound it threatened to tear physics apart. In 1974, Hawking made a disturbing calculation. He discovered that black holes aren't completely black. They emit radiation. This Hawking radiation meant black holes eventually evaporate, disappearing completely from the universe. Here's the problem. What happens to the information that fell into the black hole? A book falls into a black hole. That book contains information, the arrangement of atoms, the words on pages, the molecular structure. In quantum mechanics, information cannot be destroyed. It's a fundamental law. But if a black hole evaporates completely, where does that information go? This became known as the black hole information paradox. It represented a direct contradiction between quantum mechanics and general relativity, the two pillars of modern physics.
Look at your hand. The atoms, the molecules, the very fabric of reality itself. What if I told you that everything you're seeing right now, your hand, this screen, the stars above, is fundamentally two-dimensional information projected into three dimensions? That the universe itself might be the most elaborate hologram ever conceived. In 1997, physicist Juan Maldacena proposed something that seemed impossible. He suggested that our three-dimensional universe, with all its depth and substance, might be encoded on a distant two-dimensional surface, like a cosmic holographic projection. Most scientists dismissed it as mathematical curiosity. They were wrong. Over the past 2 decades, evidence has emerged from black hole physics, quantum experiments, and the very structure of spacetime itself. Evidence that refuses to go away. Evidence that grows stronger with each new observation. The implications are staggering. If true, everything we understand about reality, about dimension, about the nature of existence itself requires complete reconsideration. Today, we journey through evidence that challenges everything we thought we knew about the fabric of reality. Dramatic pause. Prepare yourselves. We begin.
The story begins not with the holographic principle, but with a problem that haunted Stephen Hawking for decades. A problem so profound it threatened to tear physics apart. In 1974, Hawking made a disturbing calculation. He discovered that black holes aren't completely black. They emit radiation. This Hawking radiation meant black holes eventually evaporate, disappearing completely from the universe. Here's the problem. What happens to the information that fell into the black hole? A book falls into a black hole. That book contains information, the arrangement of atoms, the words on pages, the molecular structure. In quantum mechanics, information cannot be destroyed. It's a fundamental law. But if a black hole evaporates completely, where does that information go? This became known as the black hole information paradox. It represented a direct contradiction between quantum mechanics and general relativity, the two pillars of modern physics.
For 20 years, physicists wrestled with this paradox. Some suggested information was destroyed, violating quantum mechanics. Others proposed it escaped through Hawking radiation, but calculations showed this was impossible using conventional physics. Then, in 1993, Dutch physicist Gerard 't Hooft had a radical idea. What if the information wasn't destroyed or lost? What if it was never truly inside the black hole at all? 't Hooft proposed something extraordinary. All the information that appears to fall into a three-dimensional black hole is actually encoded on its two-dimensional event horizon, the surface boundary from which nothing can escape. Like a hologram on a credit card, three-dimensional information could be stored on a two-dimensional surface. Leonard Susskind, working independently, reached similar conclusions. They called it the holographic principle. The idea seemed wild, almost mystical, but it solved the information paradox elegantly. The information wasn't destroyed because it never went inside the black hole. It was encoded on the surface all along.
Still, this was just a solution to one problem, a mathematical trick, perhaps. The holographic principle might apply to black holes, but surely not to the entire universe. In 1997, Juan Maldacena changed everything. Working at the Institute for Advanced Study in Princeton, Maldacena discovered something remarkable within string theory. He found a precise mathematical relationship, a duality, between a theoretical universe and its boundary. In Maldacena's formulation, a hypothetical five-dimensional universe with specific properties was mathematically equivalent to a theory on its four-dimensional boundary. Everything that happened in the five-dimensional space, all particles, forces, events, could be completely described by physics on the lower dimensional boundary. The implications were immediate and profound. If this worked for this theoretical universe, could it work for ours?
The scientific community reacted with a mixture of excitement and skepticism. The anti-de Sitter conformal field theory correspondence, ADS-CFT as it became known, was mathematically beautiful, but it described a universe quite different from our own. Our universe is expanding, has different symmetries, different properties. Yet the mathematical relationship Maldacena discovered was too precise, too elegant to ignore. It had been checked thousands of ways. Every calculation matched perfectly. If you computed something in the five-dimensional space, you got exactly the same answer computing it on the four-dimensional boundary. This wasn't approximate. This wasn't metaphor. This was mathematical identity. And mathematical identities in physics often reveal deep truths about reality.
But here's what troubled physicists most. If our three-dimensional universe is actually a holographic projection from a two-dimensional surface, where is that surface? What's doing the projecting? The most common proposal placed this cosmic screen at the very edge of the observable universe, on what's called the cosmic horizon, roughly 46 billion light-years away in all directions. Everything we experience, every atom in your body, every star in the sky,
would be encoded on this impossibly distant surface. Think about that. You're not really three-dimensional. You're a two-dimensional pattern being projected inward. But the evidence forces us to confront an uncomfortable possibility that this isn't merely theoretical speculation, but a fundamental description of reality itself.
If we live in a holographic universe, there should be evidence, observable signatures that distinguish a holographic reality from a real three-dimensional one. In 2008, physicist Craig Hogan at Fermilab made a startling prediction. If space-time is fundamentally holographic, it shouldn't be smooth at the smallest scales. Instead, it should exhibit a kind of graininess, quantum jitter, arising from the projection process. Hogan calculated that this jitter would manifest as extremely subtle vibrations in spacetime itself, occurring at scales far smaller than atoms, but potentially detectable with precision instruments. To test this, Hogan's team built the holometer, two 40-meter-long interferometers designed to detect holographic noise. These instruments could measure spacetime fluctuations at scales approaching the Planck length, roughly 10 to the minus 35 meters.
The holometer ran from 2014 to 2015. Scientists discovered something unexpected. While they didn't find holographic noise at the specific frequency Hogan predicted, they detected anomalous correlations in their measurements that couldn't be explained by conventional noise sources. The pattern suggested spacetime itself was exhibiting strange quantum behaviors at these tiny scales, behaviors consistent with an underlying information limit, exactly what holographic theory predicts. The results were published in 2016 in Physical Review D. While not definitive proof, they opened a new window into spacetime's fundamental structure.
But perhaps the most compelling evidence comes from black hole thermodynamics. In the 1970s, Jacob Bekenstein discovered something remarkable. A black hole's entropy, the measure of information it contains, is proportional not to its volume, but to its surface area. Think about that. A normal, three-dimensional object stores information throughout its volume. A hard drive, a book, your brain. Information is distributed in 3 dimensions. But black holes store information on their 2-dimensional surface. The formula is precise. A black hole's entropy equals its event horizon area divided by 4, measured in Planck units. This relationship has been confirmed through countless calculations and thought experiments. It's not approximate, it's exact. And it only makes sense if information is fundamentally 2-dimensional.
Scientists discovered similar patterns in the cosmic microwave background, the afterglow of the Big Bang. In 2014, researchers at the University of Southampton analyzed CMB data from the Planck satellite. They found subtle anomalies in temperature fluctuations that couldn't be explained by standard cosmological models. These anomalies matched predictions from certain holographic universe models. The pattern suggested information distribution consistent with a 2-dimensional encoding rather than purely 3-dimensional physics. The team, led by Kostas Skenderis, published their findings in Physical Review letters. They calculated that these anomalies occur at precisely the scales where holographic effects should become detectable if the universe transitions from a higher dimensional description to our observed 3D reality.
Even quantum entanglement, Einstein's spooky action at a distance, reveals holographic properties.
Recent work by physicists including Mark van Ramsdonk and Brian Swingle has shown that quantum entanglement and space-time geometry are deeply connected. In fact, space-time itself might emerge from patterns of quantum entanglement. In 2016, researchers demonstrated that the equations describing entanglement entropy and quantum systems are mathematically identical to equations describing geometry in the holographic correspondence. This suggests something profound. Space-time isn't fundamental. It emerges from quantum information encoded on a lower dimensional surface, exactly as holographic theory predicts. But this represents just one piece of a much larger puzzle hidden in the mathematics of reality itself. The evidence becomes stranger when we examine the limits of information itself. In 2020, a team at the University of California, Berkeley made a breakthrough. They calculated the maximum amount of information that can be stored in any region of space. The answer? It's proportional to the surface area of that region, not its volume. This is called the Bekenstein bound, and it applies universally. Whether you're talking about a room, a planet, or a galaxy, the maximum information capacity scales with surface area. Why would a three-dimensional universe have a two-dimensional information limit? The only explanation that makes sense is if those three dimensions are projections of two-dimensional information. The universe isn't constrained by surface area. It is surface area, projected to appear three-dimensional. The most remarkable discovery involves the behavior of gravity itself. In 2009, physicist Erik Verlinde proposed something radical. Gravity isn't a fundamental force. It's an emergent phenomenon arising from the holographic nature of spacetime. Verlinde showed that if information is fundamentally holographic, gravity naturally emerges from entropy gradients. Just as temperature differences cause heat flow, information density differences would cause what we perceive as gravitational attraction. The equations matched Einstein's theory exactly. But Verlinde made testable predictions. His modified theory predicted different behaviors for gravity at galactic scales, behaviors that might explain dark matter without requiring exotic particles. In 2016, Verlinde published detailed predictions. Then, in 2017, astronomers analyzed data from over 33,000 galaxies. The results, published in monthly notices of the Royal Astronomical Society, showed gravity behaving exactly as Verlinde's emergent theory predicted, not as standard general relativity suggested. The gravitational effects we attribute to dark matter might be signatures of holographic spacetime itself. This doesn't prove dark matter doesn't exist, but it suggests an alternative. What if the missing mass in galaxies is actually missing because we're miscounting dimensions? Recent quantum experiments add another layer of evidence. In 2019, physicists at the University of Vienna created quantum states that exist in superposition across different spatial locations. When they measured these states, they found information capacity limits consistent with holographic bounds, not three-dimensional expectations. The experiment involved creating complex, entangled states across a lattice structure. As they increased complexity, they hit a maximum information density, a ceiling that matched holographic predictions but violated three-dimensional intuition. Lead researcher Czoslaw Bruckner noted, "It's as if the universe is telling us there's a fundamental limit to how much realness can exist in a given space."
Perhaps most disturbing, physicists have discovered that the laws of physics themselves appear simpler and more fundamental when written in lower dimensions. The standard model of particle physics is notoriously complex in 3 spatial dimensions, requiring 19 free parameters that must be fine-tuned. But when physicists translate these laws using holographic methods, many complications vanish. The universe appears more elegant, more beautiful, more mathematically consistent when viewed as a lower dimensional system. This suggests something profound. Maybe the universe doesn't choose to be holographic. Maybe holography is the only way complex, information-rich universes can exist at all. The evidence extends beyond black holes in quantum mechanics into the realm of spacetime's fundamental structure, suggesting our dimensional intuitions are simply wrong.
Perhaps most disturbing, physicists have discovered that the laws of physics themselves appear simpler and more fundamental when written in lower dimensions. The standard model of... So what does it all mean? How do we put these pieces together into a coherent picture? According to the holographic principle, our universe is a projection from information encoded on a distant two-dimensional surface, likely at the cosmic horizon. But this isn't like a movie projection or a hologram on a credit card. The projection is reality. There's no real three-dimensional universe being copied. The hologram is all there is. Think of it this way. When you play a video game, the graphics on your screen represent a three-dimensional world computed from code. That code is fundamentally one-dimensional, just numbers and memory. But the world you see appears three-dimensional. Similarly, our universe appears three-dimensional, but the fundamental information, the code of reality, exists in 2 dimensions.
Leading physicists like Leonard Susskind argue that this resolves multiple paradoxes simultaneously. It explains the black hole information paradox. It explains why entropy scales with area. It explains why quantum entanglement and space-time geometry are connected. It potentially explains dark energy and dark matter. Most importantly, it provides a framework for reconciling quantum mechanics and general relativity, the holy grail of theoretical physics. But not everyone agrees on the interpretation. Some physicists, including Rafael Bosso at Berkeley, argue the holographic principle applies only to specific regions of spacetime bounded by horizons. The entire universe might not be holographic, only portions of it. Others, like Ted Jacobson, suggest holography reveals something deeper, that thermodynamics and information theory are more fundamental than space-time itself. Space and time emerge from entropy and quantum information. There's also the question of which dimension is real. Are we three-dimensional beings encoded in 2 dimensions, or are we 2-dimensional patterns that merely experience 3 dimensions? The mathematics doesn't distinguish. Both descriptions are equally valid, equally real. This forces us to reconsider fundamental assumptions about the nature of reality itself. Dimension might not be a fundamental property of the universe. Instead, dimensionality might be emergent, arising from how information is organized and processed. Your experience of 3-dimensional space, of depth and volume and distance, could be how a fundamentally 2-dimensional information pattern interprets itself. You're not in a hologram. You are the hologram. So where does the evidence lead? What technologies and observations might definitively prove or disprove the holographic universe?
Several experiments are currently underway. The Laser Interferometer Space Antenna, LISA, scheduled to launch in the 2030s, will detect gravitational waves with unprecedented precision. If spacetime is holographic, gravitational waves should exhibit subtle signatures, tiny radiations from smooth propagation that reveal spacetime's fundamental graininess. Researchers at the Max Planck Institute for Gravitational Physics are developing the theoretical framework for what these signatures should look like.
Recent breakthroughs in quantum computing offer another avenue for testing holographic theories. In 2022, physicists at Google and Caltech used a quantum computer to simulate a holographic wormhole, a connection between two regions of space-time. While microscopic and not a traversable wormhole, the experiment demonstrated that holographic correspondence principles work in real quantum systems, not just theoretical mathematics. Lead researcher Maria Sparopoulou noted, "We're learning to probe the holographic dictionary, the translation between bulk spacetime and boundary information. Future quantum computers might simulate entire regions of holographic spacetime, allowing physicists to test predictions impossible to observe directly." The implications for space exploration and physics extend into practical realms. If gravity is emergent from holographic information, it might be possible to manipulate gravitational fields by controlling information density. This sounds like science fiction, but it's a logical consequence of emergent gravity theories. Researchers at the University of Amsterdam are exploring whether local information manipulation could produce measurable gravitational effects, essentially creating tiny gravitational anomalies in laboratory settings. The experiments are extraordinarily sensitive, searching for effects billions of times smaller than Earth's gravity. But if successful, they would prove that gravity can be engineered through information control. What this means for humanity's understanding of our place in the cosmos is profound. If we're holographic projections, it suggests consciousness itself might be a holographic phenomenon, a pattern of information processing that exists simultaneously in multiple dimensional descriptions. This doesn't mean we're not real. It means real is more subtle, more strange, more wonderful than we imagined. Some physicists speculate that the holographic nature of reality might explain quantum consciousness proposals. Ideas suggesting consciousness arises from quantum processes in the brain. If the brain processes information holographically, accessing both local and non-local quantum states, it could explain subjective experience in ways conventional neuroscience cannot. The most speculative implications involve the ultimate fate of information itself. If the universe is holographic, information is truly fundamental and indestructible. This means everything that ever happened, every thought you've ever had, every moment of existence is permanently encoded in the cosmic hologram. Nothing is lost. Everything persists as pattern, as information, as structure encoded on the universal boundary. In a holographic universe, the past doesn't vanish. It remains encoded, theoretically accessible, forever part of reality's information content. We must now confront the most mind-bending implications of holographic reality. If our universe is a holographic projection, what exists outside the hologram? Is there a higher dimensional reality from which our universe is projected? Some theories suggest yes. In certain models, our three-dimensional universe is the holographic boundary of a four-dimensional bulk spacetime. Everything we experience is surface physics of a deeper, hidden reality. But here's the twist.
That four-dimensional bulk might itself be holographic, a projection from an even lower dimensional surface. It's holograms all the way down, or up, or sideways through dimensions we cannot perceive.
The most profound implications emerge when we consider consciousness and observation. Quantum mechanics tells us observation affects reality. The holographic principle tells us reality is information. Combined, they suggest something extraordinary. Consciousness might be how holographic information observes itself. You're not separate from the hologram examining it from outside. You're a self-aware pattern within the hologram, capable of perceiving other patterns, including the holographic nature of your own existence. This resolves certain quantum paradoxes. The observer isn't separate from the observed because both are patterns in the same holographic information field.
Then there's the question of simulation. If our universe is holographic, fundamentally computational at its core, does that make it a simulation in the traditional sense? Are we living in an artificial reality created by some advanced civilization? The holographic principle suggests a different answer. The universe might be naturally computational without requiring a simulator. Information processing and physical reality might be the same thing, viewed from different perspectives. The universe computes itself. We are the computation computing itself. Reality is information becoming aware of its own structure.
Finally, we must address what the evidence suggests about reality's ultimate nature. Every indication points toward information being more fundamental than matter, energy, space, or time. These familiar concepts emerge from information, not the other way around. This means the universe's ultimate constituents aren't particles or fields or dimensions. They're bits, units of information, either encoded or decoded, processed or unprocessed, entangled or separated. Physics becomes information theory. Reality becomes data processing. Existence becomes computation. Multiple possible futures emerge based on this evidence. In one future, we develop technologies that manipulate the holographic code directly, editing reality at its most fundamental level. We become engineers of the cosmic hologram, capable of creating pocket universes, manipulating gravitational fields, even transferring consciousness between different information substrates. In another future, we discover the holographic universe is itself nested within deeper layers of reality, an infinite hierarchy of information encoding information, each layer convinced it's fundamental. In yet another, we find that consciousness can access the full holographic description, allowing direct perception of reality's information content, transcending dimensional limitations entirely. We've journeyed through evidence from black hole physics, quantum mechanics, cosmology, and information theory. Evidence that independently points toward the same radical conclusion. Our three-dimensional universe might be a holographic projection from two-dimensional information. The mathematics is precise. The evidence is mounting. The implications are profound. We began by asking, what if everything we know is fundamentally different than it appears? The evidence suggests, yes, reality's true nature is stranger, more beautiful, more elegantly mathematical than our intuitions suggest.
Current scientific consensus remains cautious but increasingly open. The holographic principle has moved from speculative theory to serious physics backed by mathematical proofs and observational hints. Most physicists now accept that black holes are holographic,
Many accept that quantum entanglement and spacetime are deeply connected. A growing number consider the entire universe might be holographic. The question is no longer, could we be holographic, but how holographic are we?
What remains unknown exceeds what we've learned. We don't know which dimensional description is fundamental. We don't know if consciousness plays a role. We don't know if the holographic universe is itself embedded in something larger. But we've glimpsed something extraordinary. Reality might be a cosmic computation, information rendering itself into existence, the universe observing itself through patterns we call consciousness. You are information that knows its information, a hologram aware of its holographic nature. And that might be the most profound truth of all. The universe is vast. The mysteries are endless. The journey continues. But now, when you look at your hand, you're seeing something new. Not solid matter, but information. Not 3 dimensions, but a projection of 2. Not a thing, but a process. Reality computing itself into being. Welcome to the holographic universe.